Namaste. Welcome to the lecture series on the subject Basic Thermodynamics, Module 1, Fundamental Concepts and Definitions. This is lecture number 3. Myself, Dr. nsatheeshkumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Benjanapadam. So the contents for this lecture 3 are classification of properties, thermodynamic state process, point function versus path function, quasi-static process, and thermodynamic cycle. So the properties are the variables which determines the state of a or the exact condition of a substance or the system. So this we discussed in the lecture number 2, and also we studied each of these properties. Now let us see how these properties are classified. So there are two classifications. One is called as extensive property. So what are the extensive properties? So the properties of the system whose value for the entire system is equal to the sum of their values for the individual parts of the system. So this is called as extensive, where the properties of the system whose value for the entire system is equal to the sum of their values for the individual parts of the system. Now let me take an example here. Suppose if you consider this box as the system. Now let me take volume, or I'll split this into different compartments like this, right? Some number of compartments. Okay, here 6 compartments like this. Now volume of this compartment is V1 and volume of this compartment is V2 and so on, V3, V4, V5 and V6. Now here you see the whose value of the entire system means what? It's total system. If I want the total volume of the system, then what I should do? I should add the volume V1, V2, V3, V4, V5 and V6. So is it a extensive property? Yes, because whose value for the entire system is equal to the sum of the values of the individual parts of the system. I hope it is very clear for you. So any property, right, whose total value is the sum of the values of the individual parts. So you can take any property for that matter and you can find out. Now examples are given. Kinetic energy. So kinetic energy, again, because it is depending upon the molecules, so each part you have to add potential energy, internal energy, total volume, total mass and enthalpy. So all these are the extensive properties. Now total volume is extensive property because it is a total, but specific volume is not extensive property because it is per kg, volume per kg. So at that, if you measure in V1, V2, V3, V4 at any compartment, volume per mass will be remaining same. Now coming to the extensive property, so intensive properties, it is a property of the system whose value for the entire system is not equal to the sum of their values for the individual parts of the system. So here the extensive property, you can see here, it depends on the mass, right? So it depends on the mass of the system. That is one of the very important characteristics of the extensive property, whereas the intensive property does not depend. So here it is not equal to the sum. The value for the entire system, is not equal to the sum like in the previous case. So here you need not add. So let you just imagine that same example where I have drawn a system and I split into individual parts. Now if you want to know the temperature of the system, do you measure the temperature at each of these compartments and you need to add that? No. If you measure the temperature at one compartment, all other compartments are also same temperature, because you just imagined or split into imaginary parts. So you need not add the temperature. Similarly the pressure, density, specific volume, so they will be same at every compartment. Hence, so at every part of the system its value will be same, so no need to add up. That is called as the intensive property. Okay, so this is a example shown: mass, volume, temperature, pressure, density. So extensive properties. mass and volume, intensive properties, temperature, pressure and density. Now thermodynamic state of a system or substance. So it is very simple. The exact condition of a system or substance is called as its state. So here if you look at the diagram 1, this is called as state 1. So the state 1, mass is 2 kg because it is a piston cylinder arrangement. So piston is here. So no mass can move out. It's a closed system. Temperature at this instant is 20 degrees Celsius and volume is 1.5 meter cube. So it is written suffix 1 to indicate temperature and volume, to indicate that the values are at the state 1 because it is the state 1. Now due to some thermodynamic process, maybe heating, cooling or some other process, you can see the piston or some external or work is done by this system. Then you see piston is displaced. You can see second diagram, the piston from this position, now it is moved to this position. So there is a displacement of the piston. That means some work is being done by the system. Maybe during this process, you see temperature has not increased, but volume will be automatically increased because the piston has displaced. So the same mass 2 kg is occupying a more volume now. So volume has increased. Now, so one of the parameters has changed, one of the variables, which is that the volume has changed its value. So then we call it as the system has undergone a change of state. Now here this is called as one state, state 1, whereas this is the state 2. So variables, they will have different value. All the variables need not have the different value. If any one of the variable changes, so then automatically the system changes to another condition. So that is what we call it as the exact condition of a system or substance is called as the state. Okay, now let us move on to the next topic. State diagram. So this is a diagram on Cartesian coordinates with any two independent properties being represented on the x and y axis. This diagram represents the state of a system at different instants. State diagram. So it is a diagram on Cartesian coordinates. So you should have a x-axis and you should have an y-axis. And here two independent properties should be represented on this two axes, that is x and y. Now here I can mark entropy and here I can mark temperature. So then it is called as temperature entropy diagram. So by knowing the values of temperature at each and every state point, I can represent that point here on this diagram, which is called as the state diagram. Similarly, I can show pressure and volume. Pressure on y-axis and volume on x-axis, then it is called as PV diagram. Similarly, you can mark pressure enthalpy, temperature enthalpy, pressure temperature, temperature volume. So any two independent properties, if you take up and if you represent that on these two axes, so then this diagram or such kind of diagram is called as the state diagram. So all this thermodynamic process analysis will be done using this state diagram. Now what is the state point? This is a point on a state diagram showing the condition of a system at a given instant in terms of the two independent properties selected on the x and y axis. So a point on the state diagram. So state diagram just now you have seen, right? So there showing the condition of a system. Suppose if you know the pressure and volume, right? So if I have a PV diagram here, so this is pressure here and here is the volume. Okay. Now if you know the pressure, maybe this is 1 bar, 2 bar, 3 bar like that, 4 bar, volume 0.5 meter cube, 1 meter cube, 1.5, 2 like that. Suppose it is 1.5 and 2 bar means you will get a point here. You see here intersection of that. So this is called as the state point. So this represents the state. Now it may be somewhere here also 0.1 bar and the 0.5 meter cube, or it may be here also. So anywhere it may be here 1 meter cube and near to some around 3.5 bar like this. So this is called as a state point. So a point on the state diagram showing the condition of a system at a given instant. So that is called as the state point. Okay, now let us move on to the next topic. So there is a path. A path is a line joining the successive state points on a state diagram. Now, as I discussed in the previous slide, I told you that whenever the properties of a system changes, so then we say that the system has undergone a change of state. Means it is moving from one state point to another state point. So how do you represent this, the change of state? For that you should have a line joining these successive state points on the state diagram. So the locus of such series of such states points through which the system passes is called as the path between the final state and the initial state. Suppose, let me draw a diagram here, the state diagram. So I can mark a point here, I can mark a point here, I can mark a point here. Now if I connect these points like this, so then it's called as the path. So this is state 1, this is state 2. So between state 1 and 2, so it is passing through the successive state points. Okay, so locus means the line connecting that, or the path from state 1 to state, all such state points. So that is called as the path. I hope it is clear for you, right? So a line joining successive state points on a state diagram during the change of state. It's nothing but the locus of series of state points through which the system passes between the initial and the final states. Now, thermodynamic process. So first of all, you should know what is state. State is nothing but the exact condition of a substance which is determined by the property values at that point. Now whenever the property values changes, we say that the system has undergone a change of state. So that is nothing but a process. So when one or more, so try to understand this point, when one or more of the thermodynamic properties of a system change, so that is what I said earlier. So any of the pressure may change, temperature may change, volume may change. So if any of these one or two or more properties changes, so we say that, so there is a change of state because we cannot represent the state point at the same location. Automatically the state point changes. You see here. Now this is the state 1 where volume is V1 and pressure is P1. This is P1 here. Now because of some thermodynamic process, the state point has moved to state 2, final state, where volume is 2 and pressure is 2. So both the pressure and volume has changed. So whenever one or more of the thermodynamic properties of a system change, so what is changed here? Pressure has changed, volume has changed. As a result, the state point has changed. So when the properties change, we say that it is a change of state. So this change of a system is referred as, change of state of the system is referred as thermodynamic process. Now the diagram you can see, so to explain that, he has taken up a piston cylinder arrangement. So initially the piston will be at this point, that is at the initial state 1, and after compression you can see the arrow mark, external work is done on the system. Because why it is called as external work? Because somebody from external to the system. System is nothing but this piston cylinder arrangement, this dotted part. Earlier the system was here, so dotted line should come up to here like this, you see, from here to here. Total, full. This is system, initial system. Now system, your boundary is flexible because piston can move or slide left to right. So that is why it is called as the flexible system. So initially system was here and this was the state 1. When some external work is done, because something or some external agency should push the piston. So this is what we call it as work is done on the system, because some external agency should push the piston. If the system itself is pushing the piston in this from left to right, so then we call it as work done by the system. So that we will discuss later about the works, conventions and all. So time being, understand that whenever a change of state takes place, so we refer to it as thermodynamic process. Now point function versus the path function. So any quantity whose change is independent of the path is a point function, and it is called as the property. The quantity, the value of which depends on the path followed during a change of state is called as the path function. So any quantity whose change is independent of path is a point function, and this is called as property. The value which depends on the path followed during a change of state, so then it is called as the path function. Now you can see here state 1 and state 2 in this diagram. This is state 1, this is the state 2. Now there are two processes which leads to state from state 1 to state 2. So if you move along this process A, so 1 A 2, so that also brings the system to point 2 or state 2. If you move along this path, that is 1 B 2, so then also the system changes its state from state 1 to state 2. Now here, what is the volume? 2 meter cube. V1 is 2 meter cube. What is the volume here? V2, 5 meter cube. So what is the change in volume during the process 1AB? If you look at this 1AB, what is the change in volume? 5 minus 2, it is 3 meter cube. So delta VA is 3 meter cube. But during this process, the work along this path is 8 kilojoules. So work done during the process 1A2 is 8 kilojoules. Now if you come along the path 1B2 like this, so once again the change in volume is 5 minus 2, it is 3 meter cube. But work done is different because path is entirely different. So work done along the path B is totally different. Now from this what you can understand is, for volume, though the system has traversed along 1A2 or 1B2, the change in volume will be remaining same. Whereas for the work, it is different for path A and path B. So what you conclude is, here volume is a point function. So it doesn't depend whether you moved along A or along B. However you reach from state 1 to state 2, because they are the fixed point, 1 and 2 are the fixed points, so change in volume will be same. But if you come to the work, what is happening, you see, work done along the path 1A2 is 8 kilojoules, whereas work done along the path 1B2, that is WB, is 12 kilojoules, means it is depending on the path. So here whichever the property which depends on path is called as path function, and whichever the property it is independent of path is called as the point function. So for a pressure which is a point function, so if you want to find a pressure change between the during the process 1 to 2, so integration 1 to 2 dp is can always written as P2 minus P1, because it is a point function, it's a property. Similarly volume, so for any point function you can write the change in property as the integral of that change between those two state points, that is 1 to 2 dV is equal to V2 minus V1, you can write. But for work you cannot write, because work during the path or change of state from 1 to 2 dW, you cannot write as W2 minus W1, because W2 is meaningless, because work is a path function, so it cannot be expressed at a point. So work is done whenever a system undergoes a change of state. Try to understand this. See, work and heat transfer takes place when the system undergoes a change of state. So there is no meaning for the work at a particular state point, right? So there is no meaning for W1, there is no meaning for W2. Hence this change in work, change of work, so during this process or work done during the process 1 to 2 we call usually, so this is the 1 to 2, integration 1 to 2 dW cannot be written as W2 minus W1, it should be written as W from 1 to 2, means W during the process 1 to 2. Similarly for the heat transfer, you should write it as integration from 1 to 2 dQ is equal to Q1 to 2, means indicating that heat transfer during the process 1 to 2. Okay, so this is how you have to write the mathematical expressions for the point functions and the path function. Now quasi-static process. So a quasi-static process is one in which the deviation from equilibrium is infinitesimally small. All the states through which the system passes during a process can be considered as a succession of equilibrium states. Now you can see the system here is a piston cylinder arrangement, you can see here. Now this is the state 1, you see the point, and it's loaded with the piston and also some weights, you can see. So these are the weights placed on the top of that. Now if I remove all the weights all together at once, then what happens? Because of this removal of weight, the piston is suddenly displaced and it will come to this point, which is called as state point 2, and this is called as state point 1. Now this is 1, the initial state, and once the weight is removed, volume has increased, pressure has decreased, so it moved to 1 to 2. So I can connect it between 1 and 2, but these points along the 1 and 2, when connected in that instant, will not be the equilibrium points, because equilibrium points achieved only at 1 and then directly at 2. So in between you don't have any equilibrium points. Such process is not called as quasi-static process. So then what is the quasi-static process? So for that, what you do is first locate the point 1. Now piston and these weights are intact, and locate point 1 here. This is here, locate 1. Now remove one of the weights. Don't remove all the weights at once. So first weight is removed. So the system expands a bit, volume is increased, pressure decreased, you mark the point 2. Now remove the second weight and you will come to this point. So each of these points are equilibrium, because as soon as the weight is removed, so piston moves a bit up because of the expansion of the gas, and it becomes to equilibrium position, means it comes to rest at that point. So when the external pressure force applied on the piston becomes equal to the internal pressure, so at that point it will be equilibrium point, because these two should be equal, the pressure, external applied pressure and the internal applied pressure, then only piston will come to rest. You see, if one of the pressure is less, so it will move in the direction of that lesser pressure. It will move in the direction of the lesser pressure. Okay, now so we removed 2 weights. Now remove one more weight, third weight, so you will move to this point. Similarly, you remove 4th weight. So each successive removal of the weight, you will get successive state points along this path, and finally when you connect these points and reach to point 2, so that is called as the quasi-static process. So that is the quasi-static process, wherein the deviation from the equilibrium is very, very small, because you removed each of these weights one by one, allowed the system to come to its equilibrium point. So the deviation from equilibrium is very, very small, and all the states through which the system passes now is considered as the equilibrium states. So this is the equilibrium state, this is also equilibrium state. You see, all these are the equilibrium states, and when all the points are equilibrium states, the process or the connecting path which represents that process is called as the quasi-static process. So very, very important. So in a quasi-static process, all the points will be the equilibrium points. Okay. Okay, now thus the quasi-equilibrium process takes place very slowly if one property remains constant during a process. Now, so this is what we studied about the quasi-static process, wherein every state point along that path is a equilibrium state. Now, there are different processes, thermodynamic process, based on the change in property. Now, if one of the property remains constant during the process, if the temperature may remain constant during the process, pressure may remain constant during the process, volume may remain constant. So accordingly, you call by different names by using a prefix called as iso. So what are they? If the temperature remains constant, we call it as isothermal process. If the pressure remains constant during the process, we call it as isobaric, and if the volume remains constant, we call it as isochoric process. So constant temperature isothermal process, constant pressure isobaric process, and constant volume isochoric process, right? So this is how the prefix iso is used to indicate that a property remains constant during the process or change of state. Now coming to the reversible and irreversible process in depth we will be studying later. Just we will have a idea of this, what is reversible and irreversible process. A process is called a reversible process if it can be completely reversed and the system and the surroundings come back to its original state. A process is called a reversible process if it can be completely reversed and the system and the surroundings come back to its original state. Now let me take the example of this piston cylinder arrangement. So cylinder and this is the piston. Now imagine that I do some heating of this system, external heat supplies, maybe some 10 kilojoules of heat is supplied. Now during this process these molecules absorb energy, they energized, so it starts exerting more pressure on the walls, but the piston is flexible to move, so it moves upwards by doing some 8 kilojoules of work. Now let us assume that there is no friction. Okay. Now if there is no friction, so 8 kilojoules of work is done, so remaining 2 kilojoules of energy remains within the system. That means it leads to increase in internal energy of the system by 2 kilojoules. This is what I told you earlier also. Change in internal energy of the system can be found out. So you supply 10 kilojoules and the work is done is 8 kilojoules. So remaining 2 kilojoules remains with the system itself, helps to increase its internal energy. Now if I reverse this process by doing 8 kilojoules of work on the system, then if 10 kilojoules of the heat is removed from the system, then system will come back to its initial state. And even the surroundings, why 10 kilojoules is supplied from the surroundings, 8 kilojoules work is done, so there is a loss of 2 kilojoules for the surroundings, which will remain inside the system as internal energy. But during the reverse process, when 8 kilojoules of work is done, including this 2, 10 is coming out, means whatever the surroundings has given initially, now it's coming back to the surroundings. So both the surroundings and the system come back to its initial state. So this is called as a reversible process, means both are coming to its original state. But in reality, what happens is, now when the heat supplied is 10 kilojoules initially, 8 kilojoules of work is done, this internal energy is not just 2 kilojoules, it will be more than 2 kilojoules, because there will be friction between the system, piston and the cylinder, which adds up to some heat to this. So this will be more than 2 kilojoules, maybe some 2.2 kilojoules. The internal energy increase will be 2.2 kilojoules. So friction has contributed to some heat, just an assumption, some point to his assumption. Okay, friction, contribution of the friction to the heat. Okay, now if I do the 8 kilojoules of work back to the or on the system and 10 kilojoules is removed, now again friction will add 0.2, so 0.4 kilojoules of heat, 0.4, okay, 0.4 kilojoules of heat will be remaining within the system, means system will not come back to its initial state. Is it understand my point? You are doing 8 kilojoules of work on the system, same 10 kilojoules you are removing, already 0.2 is added as internal energy in the upward movement of the piston, again 0.2 added during the downward because of the friction, so 0.4 is additionally added during this process. Will the system come back to its initial state? No, its internal energy has increased. Surroundings has come because it has given 10 and it has got 10. But suppose if you are compressing this further to remove this 0.4 kilojoules further, then you have to need extra work. That means surroundings will not come to its initial state. So then its system is not a reversible process. So your second example what I gave is for irreversible process, means either the system or the surroundings doesn't come back to its initial state. So a process which cannot be exactly reversed and the system cannot be brought back to its initial state without leaving a net change in the surroundings is called as irreversible process. So system should be brought to its initial state, but it should not leave any change in the surroundings. But in the second example what I told, you can make the system to come to its initial state, but some additional heat will be transferred to the surroundings, 10.4 instead of 10. So some net change is there in the surroundings. So that is not possible for a reversible process. Such process is called as the irreversible process. Now coming to the last topic of this lecture, it is nothing but thermodynamic cycle. So you studied state, the exact condition of a substance, then you studied process, now the cycle. When a number of processes in sequence bring the system back to its initial state, then the system is said to undergone a thermodynamic cycle. Try to understand this process. When a number of processes in sequence, so one thermodynamic process changes the state from 1 to 2, so process is 1 to 2. From 2, it again undergoes a change of state to 0.3, process is 2 to 3. From 3, again it undergoes a change of state to 0.4, so process is 3 to 4. From 4, it comes back to state 1 and the process is 4 to 1. Then we call it as a cycle. Now you can see, look at this temperature entropy diagram here. So this is the point 1. So there is a process 1 to 2 and the system undergoes a change of state. Now this line is vertical and this is entropy line. So here if I draw this vertical line, it is 90 degree. S1 is equal to S2, means it is a constant entropy process or isentropic process. Then 2 to 3, again change of state here, it comes to 0.3 and we is written that volume is constant, so it is a isochoric process. Then 3 to 4, again change of state is there, so 3 to 4 is a process, so state point is 4, 3 to 4 is isentropic process again, and 4 to 1 again is a constant volume process, isochoric process, and system come back to its initial state 1. So a succession of process. What are the succession of process? 1 to 2 first, then 2 to 3, then 3 to 4, and then 4 to 1. So this sequence of this process bringing the system to its initial state, so then the system, you can say that the system has undergone a thermodynamic cycle. Okay. So in the figure 1, 2, 3, 4, 1 is the cycle consisting of 4 processes. Okay, for a cycle the change in property is same, 0. Okay, because it was initially at state 1, after undergoing the sequence of process it has come back to its state 1. So initial state and final state is same for a cycle. So if the initial state and final state is same, so there is no change in any of the properties of the system. That means change in value of any property is 0. Try to understand this point, very very important. So change in value of property, any property value is 0 for a cyclic process. Okay. So with that we will conclude the lecture number 3 of module 1 under the subject basic thermodynamics. So we will continue with the lecture number 4. Thank you.